Hello and welcome to this Danfoss Drives training course. In this course we will present MyDrive Harmonics, an online tool to calculate harmonics in a system and design the optimal harmonic mitigation solution to meet specific requirements. MyDrive Harmonics is a professional harmonic simulation tool that lets you determine whether harmonics will be an issue in your installation when drives are added. It estimates the benefits of adding various harmonic mitigation solutions from the Danfoss product portfolio and calculates system harmonic distortion. It is the ideal solution if you are planning to extend your existing installation or if you are planning a new installation from scratch. It uses a built-in power circuit simulator that performs a simulation of the specific system designed by the user and supports all Danfoss drives. It can display the results as pass-fail compliance compared to the selected standard. The results can be saved as a report in either PDF format or it can be exported to Excel for further analysis. MyDrive Harmonics is a web-based tool, so there is no need to install any software on your PC or device. Simply open up a browser window in Chrome, Edge, Safari, or Firefox and go to harmonics.mydrive.danfoss.com. A web page like the one shown here will open. There are two versions of this tool, Basic and Premium. The Premium features are available after the Premium version has been ordered. The status of a subscription can be viewed from the Account Profile button. A 30-day free trial of the Premium version can be selected before making a final decision to purchase a subscription to MyDrive Harmonics. You do not need to add your payment details to use the 30-day trial. A few days before the trial ends, you will receive an email with instructions on how to continue using the Premium version by adding your payment information. A subscription for the Premium version lasts 1 year, after which it can be renewed. The Premium version allows all the functions of the basic version, and adds the ability to create cables based on manufacturer specs and specify the cable length. Add non-Danfoss drives based on the drive specs and the ability to use them with Danfoss products in the same simulation. Use custom user-defined standards that can be reused in all projects, allowing you to easily adapt to specific regional needs. Create diagrams of your system automatically, which are included in the PDF reports. These diagrams allow detailed measurements at various points in the system. The ability to create large systems, allowing multiple systems in one project. Medium voltage systems can also be created. Optimize active filters by defining them in more detail by power factor correction and compensation ratios. This feature is also available for non-Danfoss filters. Click the Sign In button to log in or to create a new Danfoss profile. Your Danfoss profile can be used for all Danfoss applications where you see this login screen. To subscribe to the Premium version, click the diamond icon on the left and follow the link to buy MyDrive Harmonics Premium or go to suite.mydrive.danfoss.com. I have a Danfoss internal subscription which gives me access to the Premium features. This demonstration will be displaying some of these Premium features. To view or edit a previously saved project, click on Load Project. To start a new project, click Create Project. You can also click on the plus button to create a new project. A window will pop up and will ask for the project name and other related information. I have created this simplified customer line diagram that I will use in this training video. The information shown here will be used to set up the project in MyDrive Harmonics. This diagram shows a system with some non-linear loads like drives, and linear loads of motors. I converted the system into a simplified form in this diagram. The transformer has a rating of 500 kVA and a short circuit impedance of 5.5%. It has a secondary voltage of 480 volts and rated for a frequency of 60 Hz. This information was found on the transformer data label. The transformer is connected to a 100 horsepower VLT FC102 drive and 250 horsepower FC102 drives. It is also connected to a 200 horsepower chiller motor and two 20 horsepower motors connected to pumps. In total, we have a 240 horsepower or 180 kilowatts linear load. I'll click the Create Project button and start filling in the information. The first field allows you to fill in a project name, followed by the person preparing the project in the Created By field. Next, enter the name of the customer for the project, followed by the version information for the project, if desired. Two options are available for the unit system, metric or imperial. Selecting metric displays drive ratings in kilowatts, and selecting imperial displays drive ratings in horsepower. Next you can select the supply frequency for the project. You can choose either 50 Hz or 60 Hz. Because this project is in the US, I will select 60 Hz. You can enter your date the project was created and you can provide any additional comments or assumption information relevant to this project. Click on Next to continue. On this page we can add information about the system. First we will name the system. Next, we will define the system type. Either a low voltage or medium voltage system can be selected. The supply field allows selection of the type of power source for the system. Either grid or generator can be selected. The text box allows you to add an optional description pertaining to the system. Click Next to continue. Here you can select the measurement points to view the harmonics results in the system. There are 3 options available. The first selection is transformer secondary. According to the IEEE 519 standard, it is recommended to measure harmonics at the transformer secondary, and this is one of the most important points to check the system harmonics. The next selection is LV busbar. This option allows for harmonic measurement at the DC link busbar. The third selection is LV individual load. This allows measurements at individual drive loads. For this training video, we will select transformer secondary. Click Next to continue. On this page we will select the harmonic standard with which to check compliance. On this page we have the option to select the harmonic standard. We can choose from various standards including IEEE 519, IEC, or Marine. The IEEE 519 standard is available in both the 2014 version and the 2022 version. Despite the availability of the updated 2022 version, many projects still reference the IEEE 519 2014 standard. Therefore, for this demonstration, we will select the IEEE 519 2014 standard. On the next page we need to define the voltage and short circuit current ratio at the point of common coupling, or PCC. Since this is a low voltage system, we will enable the setting for the bus voltage at the PCC less than 1000 volts. Initially we will choose a short circuit current to load ratio of less than 20. This ratio is determined based on the transformer and connected load. The tool will calculate this ratio and it will be displayed in the results. Based on these results, this ratio can be adjusted at a later stage if necessary. Click Complete to finish creating the first system. In this section, we will enter all the relevant information about the customer's system and loads. This includes transformer data, specifications and capacity, characteristics of connected loads, both linear and nonlinear, specific requirements, and any particular needs that the system must meet for harmonic mitigation. By providing comprehensive and accurate data, we ensure that the analysis and result will be precise and tailored to the customer's requirements. Based on our example previously shown, we will enter all the necessary information in their respective fields. First, grid. Since we do not have any specific grid information on the upstream side, we will maintain this value at their default settings for now. Transformer information. Enter a name for the transformer. We will keep it as T11. Secondary voltage. For the United States, it's 480 volts. In our example, the transformer size is 500 kVA. Short circuit voltage. A transformer has a certain series impedance which is distributed between the primary and secondary windings. It is common practice to express this impedance in a percentage. It is often called short circuit impedance in the transformer data sheet. In our example it is 5.5%. Ohmic part of short circuit voltage. If this is not given in the data sheet, use the default value of 1.5%. As a standard practice, it is recommended to set the secondary demand current to 80% of secondary nominal current. However, if the customer has a specific percentage in mind, you can enter that value here. We will keep the default value of 80%. After we have entered the transformer information, navigate back to the previous page. We will now enter the Danfoss drive information. To do this, click on option label FC6 Pulse Group PCC11 under the Frequency Converter 6 Pulse item. On the Frequency Converter 6 Pulse page, use the plus icon to add a drive, or click on the listed drive item to edit it. Before proceeding, make sure to enable the drive by toggling the enabled switch. Next, you need to assign a designation or name to the drive. In this example, we will name it SF1. We have a quantity of 1. You have the option to choose from various Danfoss drive models. The available drives that can be selected are found by clicking on the text box under the model item. Click on the drive model to display all of the Danfoss drives that can be selected. This tool shows the latest drives available from Danfoss, including IC2 Micro, IC7 Automation, and IC7 Automation air-cooled enclosed drives, as well as the VACON 100, VACON 20, and NX series drives. This tool also includes Danfoss's legacy products like the VLT 2800, VLT 5000, and the VLT 6000 and 8000 drives. It also has the current Danfoss VLT products like FC202, FC302 and other VLT products. For our example, we will select the FC102 drive. Now we will select the power rating of the drive. This drive is rated 100 horsepower. According to the imperial setting, the power is displayed in horsepower with a nominal input current of 133 amps with a 440 to 480 volt supply. This drive currently shows a 100% load on it. If the customer specifies a different load, such as 80%, you can adjust the setting accordingly to meet their requirement. Additionally, if an AC line reactor is connected in series with the drive, include the impedance value of the reactor in the configuration here. We will not add any harmonic filters in this configuration. Let's go back to the frequency converter page. By doing this, you can see SF1 is highlighted and is active now. Next, we will add another drive by clicking the plus button. In this section, we have the option to select either an individual drive or multiple drives. To add multiple drives, you can choose one of the bundled drive selections, either with or without an advanced harmonic filter. Please note that for the FC6 Pulse Group PCC11, it is not possible to add more than 6 frequency converter drive groups or ratings. If you need to manage more than 6, please select one of the bundled options to ensure proper configuration. In the bundle, you can add as many ratings and number of drives as needed. In our example, we are using 3 drives, therefore we will select the frequency converter 6 pulse option. Next, we will choose an FC102 drive. I'll scroll through the list and find a 50 horsepower drive. Now we can enter the quantity of drives we would like to add. Since we are creating 3 different frequency converters, we will set the quantity to 1 for each of them. Finally, click the check mark to add the drive. Click on the designation text box to change the name of the drive. In our system, one of the 50 horsepower drives is labeled RF1. You can see this is now showing 50 horsepower, the FC102 model number, and 66 nominal amps at an input with a 440 to 480 volts supply. This drive will run 100% load, with no additional reactor or line filter. Click on the back button. Now we will add one more 50 horsepower drive. You can click the plus button to add a drive, or click on RF1 where we can generate a copy of this drive. Click the copy button. Now we have generated a drive labeled RF1, 2. This is identical to the 50 horsepower drive which we created earlier. We will change the designation to EXF1 as per our simplified diagram. Now we have 3 different drives in our system, SF1, RF1, and EXF1. The drive information is shown on this diagram for each item as well. We have a 75 kilowatt or 100 horsepower drive on SF1 and 2 37 kilowatt or 50 horsepower drives, one on RF1 and one on EXF1. After defining the drive loads on the transformer, we will now add other loads, in this case, the motor loads. It is important to note that motors are considered inductive loads and are categorized as a linear load. To add motor loads, we will navigate to the linear load item and select the motor option. Next, ensure the switch for the motor is in the on position. In this section, the motor load should be entered in kilowatts. If the motor loads are given in horsepower, they can be converted to kilowatts by multiplying the horsepower value by 0.7457. This conversion factor accounts for the difference in power measurement units. Additionally, it is necessary to set the nominal voltage which corresponds to the secondary voltage of the transformer. In this case, the nominal voltage is set to 480 volts. If you have information about the power factor and the load of the motor, you can enter this data in the designated fields. The power factor, or cosine phi, represents the ratio of real power to apparent power, and it is usually specified as a value between 0 and 1. The load refers to the percentage of the motor's rated capacity that it is currently operating at. If you do not have this value readily available, it is acceptable to leave the power factor and load at their default settings. In addition to motor loads, a customer may have other linear loads connected to the transformer such as a capacitor bank detuned, or a resistive load like a heater. Heaters are considered resistive, meaning they do not have inductive characteristics like a motor. To account for this load, select the option and you can enter the respective details. However, for the purpose of this training video, we will keep these options disabled. Please note that in a real-world scenario it is important to accurately assess and include all relevant loads including capacitor banks detuned, or heater loads to ensure accurate representation of the system's electrical characteristics. In addition to this wide range of linear loads option, this tool offers flexibility to incorporate other system components and filtering solutions, providing a comprehensive analysis of the electrical system. One significant feature is the ability to include active front-end solutions such as VACON, NX and IC7 modules, as well as IC70 distortion drives. The ability to add these items ensures high-quality power supply and minimized harmonic distortion in the system. For this training video, we will not add an active front-end module. This tool also supports Danfoss legacy low harmonic drives from the VLT-FC series. These drives are specifically designed to reduce harmonics and achieve compliance with international power quality standards. However, for the purpose of this training video, we will not be utilizing this option. For customers who have an uninterruptible power supply or UPS, a switch, or a regulated power supply, this tool allows for selection of these options under the nonlinear load category. This tool is also beneficial for analyzing the Danfoss turbo core compressor drives. We will not select these options in this video. By offering a wide range of system components and filter solutions, this tool empowers the user to effectively evaluate and calculate the harmonics of the system with precision. Now that we have entered all the required information in the tool based on our example, we can proceed to view the results. This tool will provide us with valuable insight and analysis regarding the electrical system performance specifically related to the entered loads and system components. The results will include key information such as harmonics present in the system. Harmonic levels are measurements of the distortion in the waveform and are crucial to assess the quality of the electrical power supply. Using these tools for calculations and analysis, we will be able to determine the specific harmonic levels at various points in the system such as the transformer, drive loads, and other areas. In addition to harmonic levels, this tool can also provide information on other critical parameters. This includes power factor, voltage distortion, current distortion and other electrical calculations. By evaluating these results, we can gain a comprehensive understanding of the system performance and identify any potential issues or areas for improvement. In our result, you can see that the transformer's secondary side voltage total harmonic distortion or THD is 4.76% and it complies with the IEEE 519/2014 standard. But for the current total demand distortion or TDD, it is 12.65%. This is higher than the requirement of the standard and why it indicates a failure. Another concern is that the IEEE 519/2014 ISC to IL ratio is less than 20, which is outside of the limit. In the calculation, we can see that the short circuit current, demand current RMS ratio is 21.45. This means we need to change the ratio in our standard configuration. To make these changes, click on the settings icon, which is the results configuration. Click on Standard Configuration, Transformer 1, and then Transformer Secondary. We have selected the IEEE 519/2014 standard, and now we need to change our ratio to between 20 and 50. Now we can see that it shows compliance with the ISC to IL ratio between 20 to 50. But it still shows a failure here. The tool shows problems at 5, total demand distortion. Go to the T11 secondary side. Scroll down. A table for current distortion is displayed here. You can see that this harmonic table shows various harmonics like 5th harmonic, 7th, 11th, and so on. On the right side under the blue heading, you can see the IEEE 519/2014 requirement. It says the 5th harmonic level should be 7 or less, but according to the result, it's 11.44%, which is higher than the standard requirement. This is why it shows failed. All of the other harmonic level values in the chart comply with the standard requirement. To meet the IEEE 519/2014 requirement, we will need to add a passive or active filter. First, we will try adding a passive filter on the drive. Passive filters are connected in series with the drive. So we will connect a filter to one of the 3 drives. As a standard practice, it is recommended to connect it to the biggest drive first. The SF1 motor is a 100 horsepower drive, so I will select a passive harmonic filter for this drive. I'll click on this drive and then scroll down to the passive harmonic filter mode, which is currently disabled. Click on the drop-down. There are 3 options here: disabled, enabled with capacitor, and enabled without capacitor. It is recommended to select enabled with capacitor. It will open the filter configuration shown here. Select a passive harmonic filter model. The advanced harmonic filter has 2 options, AHF005 and AHF010. AHF005 limits the harmonics up to 5%, and AHF010 limits the harmonics up to 10%. The AHF005 will perform better than the AHF010, so we will select an AHF005. The filter needs to be selected based on the input current of the drive. For this 100 horsepower drive, the input current is shown here, which is 133 amps. Note that the input current displayed here is based on the 380 to 415 volt rating. With a 440 to 480 volt supply, the nominal input current is 118 amps. Refer to the design guide for the VLT Advanced Harmonic Filter AHF005 and AHF010 to view the filter data and specifications. We will select the AHF005 filter with an input current of 118 amps for a 440 to 480 volt supply. Here we will select quantity 1. Go back to the main page and click on Results again. According to the results, it passed for both voltage THD and current TDD. The value is higher than 5%, but according to the IEEE 519/2014 standard, it does comply. You can also verify this by clicking the T11 secondary side information and scroll down to the chart we previously viewed. According to the standard, it should be less than 7%. The 5th harmonic is now 6.15%. This complies to the IEEE 519/2014 standard. Now we will select an active filter. First we will go back to the system and disable our passive harmonic filter. Go back to the main screen and select the active filter option. In the active filter, we have an AAF007 product. This active filter solution is available from 35 to 600 amps. If you see the result without any harmonic filter, we can determine the harmonic current of the system, which can be found in the results. Scroll down, and on the 5th row we can see the total harmonic current RMS, which is 60.87 amps. We need to mitigate the 60.87 amps of harmonic current. To do that, we will first select an active filter, AF007. Go back to Transformer 1. Select the active filter AF007. Enable this option and select the 55 amp filter. Go back to the main page and click on the results. Now the tool will calculate all harmonics in the system, including the active harmonic filter. The results show that the system passed with 5.60% current THD and 3.58% current TDD. Using the active filter gives a better result than the passive filter. To optimize this option, we can also try lowering the active filter size. To do this, go back to the active filter AAF007 and select the 35 amp filter. Next, go back to the main page and click on the results. The results show the current THD is 11.03% and current TDD is 7.06%. According to the IEEE 519/2014 standard, it is still in compliance. This shows that the 35 amp filter can be used instead of the 55 amp filter to stay compliant, while reducing the cost. If the customer is looking to upgrade a motor load in the future by adding a drive load, they wouldn't need to add any additional filtering. In this case, we would recommend selecting the 55 amp filter from the beginning, or go with the 35 amp filter now, then in the future add another drive with an active or passive filter. To download the results, click on the Download Reports button. The report will download to your PC or device. This report will download two files. One is an Excel file, and the other is a PDF file. The PDF report looks like this. It's titled MyDrive Harmonics Report, along with the name you created for your project. In our example, it's named Training Video. It shows the results and the connected loads on the transformer, along with the 90 kilowatt linear loads and the 149 kilowatt nonlinear loads. The next page shows the three different drives. The System Components page lists the linear loads, the active filter, and the three drive loads, followed by the charts and graphical reports. On the last page we'll find all of the electrical characteristics of the system. The Excel file that is downloaded can be modified and sent to the customer if system changes are required or recommended. By clicking the Disk button, the entire project can be saved to your device in a JSON file that you can use for future modifications or other needs. To open this file, click on the Load Project button from the home page, select the file, then click the Open button. Any system component can now be modified and the results process can be run again. If you have any questions or need help related to this tool, please reach out to Danfoss Drives technical support. Thanks for your interest in Danfoss Drives products. We hope this information has been helpful.